questions 8 through 10 of the 1999 grade 12 Euclid math contest. The equation y is equal to x squared plus 2ax plus a represents a parabola for all real values of a. Prove that each of these parabolas passes through a common point and determine the coordinates of that point. So we are given y is equal to x squared plus 2ax plus a. And they're saying that no matter what a is any real number, that this parabola is always going to pass through one point, one common point. So no matter what you put for a, you could put 5, 50, 1,000, whatever, this parabola is always going to have one point that it passes through, always. So since this coefficient here is 1, it's probably a parabola that points upward. So it's going to be like this, right? Something like that. And they're saying that there's always some point, wherever, let's say it's here, that this parabola will always pass through no matter what is a. So it will look different. It might look like this, or it might look like that, but that point is always going to be common. So that's what we have to figure out. So what we can do is we can set a to certain values and see what we get. So let's start by setting a to 0. If we do that, the equation just becomes y equals x squared. All right, that's simple enough. Now let's set a equal to 1. Then what do we get? Y is equal to x squared plus 2x plus 1, like that. Now, that common point is on every single parabola of this form. So that means that we can find it by setting these two equal to each other. So you'd have x squared is equal to x squared plus 2x plus 1, like that. And therefore, 0 is equal to 2x plus 1, and therefore x is equal to minus 1 over 2. Now to get our y coordinate, we can plug x equal to a half, negative a half back into any of these. So negative a half squared. So we've got 1/4. So this point, negative 1/2, a quarter, is common to all parabolas of this form, no matter what a is, for all real values of a. Now, if you're not convinced, let's try another value for a. Let's try a equals 2 and see what we get. So we have y x squared plus, this would be now 4x plus 2, correct? You're subbing a equals 2. So now let's see what we get for x equals minus a half. Minus a half squared plus 4 times minus a half plus 2. And this would be a quarter minus 2 plus 2. And this is a quarter. So we get the same value for y. All right? So no matter what you put in for a, this coordinate will always be one point on the parabola. So we proved that each of these parabolas pass through a common point, and the coordinates of that point are negative 1/2 and a quarter. Now let's turn our attention to point B. The vertices of the parabolas in part A lie on a curve. Prove that this curve is itself a parabola whose vertex is the common point found in A. All right, let's first understand what this means. So the vertices of the parabolas in part A. All right, what are the parabolas in part A? Well, they're these ones. 2ax plus a. Now you say, well, this is just one parabola. Yes, but it's parabolas because a can be any real value. So remember, a can be 0, 1, 2, whatever you want it to be. So there's many parabolas of this form. And they're saying that the vertices, so if you have a parabola, the vertice is the minimum point or the maximum point, right? This is known as a vertice or vertex. Vertex is singular, vertice is plural. The vertices of this parabola lie on a curve. So let us just concentrate on that part. Let's not go forward. Let's concentrate on that sentence and understand it and do it, and then we'll move forward. So the vertices of all of these parabolas for a equals 1, 2, 3, whatever, lie on a curve. All right, so first we need to concentrate on what is the vertice. Okay, so how do you do that? Well, before I show how you do that, I have to first show that a parabola can be written in this form. Ax minus h squared plus k. And if you write the parabola in this form, the vertex is hk. Okay? So what we have to first do is write this formula in this form, and that will help us figure out what the vertex is, what the vertices are. So let's do that. Y is equal to x squared plus 2ax plus a. Now how do we get this into this form? Well, with a little bit of fancy algebra. 2ax. All right, so now where the fanciness comes in, add an a squared and subtract an a squared, like that. And then you got your plus a. This allows you to factor this part of the equation. You got x, a, and I believe just plus and plus, like that. And then the remainder of the equation is a squared plus a. And then this becomes x plus a squared, and then plus a minus a squared, like that. And you see how it became in this form? What is hk in our scenario now? Look at it carefully. H is minus a, and what's k? A minus a squared. Correct? So I hope you understand that. All right. If you understand it, let's move forward. So now, this represents the form that all vertices have. Minus a for h and a minus a squared for k. They're saying, now let's go back to the sentence, the vertices of the parabola, which are all of this form, the vertices, lie on a curve. So if you start plugging in values for a, it will eventually lead to some sort of curve. So if I put a equals 1, it'll be -1 and 0, right? So it'll be here. And if I keep going like that, a is 0, it'll be like this, and it'll keep going, and eventually all the values of a will produce a curve. And that's what they mean, that the vertices of the parabola in part A, which was this one, lie on a curve. Okay? I hope you get that before I move forward, because I hope that you can understand what I wrote. Otherwise, the proof is not going to make sense. So, if you don't, pause it, rewind it, read it again, or watch it again. All right. So now let's move forward with the second part of the sentence. Prove that this curve that I just drew right there itself is a parabola. Well, I kind of drew it as a parabola, but we got to prove that. Whose vertex is the common point found in A. So they're saying that this parabola has a vertex. So let's use a different color here. The vertex itself is right here, the top point. And that vertex is the common point found in part A. Do you remember in part A we found a common point? And that common point, if you rewind, will reveal that it was -1/2 and 1/4. Right? So they want you to prove that. First, prove that this curve is a parabola, and then prove that its vertice is -1/2, 1/4, which was the common point in the previous question. Okay, so let's do that. So the first thing we have to do is prove that all of these points, if you plot them for a equals 1, 2, 0, whatever, that all those points when plotted will form a parabola. Okay, so how do we do that? Well, notice that the x coordinate is -a, and the y coordinate is of the form a minus a squared. So the x coordinates are of that form, and the y coordinates are of the form a minus a squared. Correct? So in order to get a equation, we've got to get rid of these a's. We've got to just deal with x's and y's. Because remember, this is x and this is y. So just substitute. We know x is equal to -a, so substitute this into this. So y will equal -x minus -x squared. Correct? Just in case you got a little confused, -x is equal to a, just from this equation right here. And that's how I was able to substitute it in. So this equals -x minus x squared. Or you can rearrange it, -x squared minus x. And this is a parabola. Parabolas have this form. Ax squared plus bx plus c, right? Parabolas always look like this. Ax squared plus bx plus c. And that's the form. In our case, a is -1, b is -1, and c is 0. All right? So we proved the first part, which is saying right here, prove that this curve itself is a parabola. And now the final part is, whose vertex is the common point found in part A? This is the vertex. So we have to now prove that this parabola has this vertex, -1/2 and 1/4. All right, so how do we do that? Well, to prove that, we've got to get this equation into this form right here. And if we can get it into that form, we can find the vertex. All right? So what I'm going to do is put that form over here on the side so you can see what I am trying to attempt. I have to get it into that form. If I get it into that form, then the vertex is HK. Okay? So let's try to get this parabola, the equation, into this form. So how do I do that? Well, something called completing the square. Some of you, I'm sure, have learned this, and this is where you apply it. So it would be -x squared minus x, and then what you do is you take the coefficient here, which in this case is 1, and you take half of it and square it. So half of this coefficient is half, right? Half of 1 is a half, and then you square that, and that gives you 1/4. And then of course you have to subtract 1/4 because you can't just add something. So this allows you to factor. First, what I'm going to do is I'm going to take out a negative, x squared plus x plus 1/4. So I grouped this, this, and this together, and then therefore this goes over here, plus 1/4, like that. And then this will allow me to factor this part here, x a half plus plus 1/4. And therefore this becomes x plus a half all squared plus a quarter. So you tell me, what is the vertex? Well, it's of this form, right? So the vertex is minus a half a quarter. And that is what they wanted you to prove. They wanted you to prove that the vertex is minus a half a quarter right there, because this was the common point that we found in part A. So there you have it. That completes number 8. A millennium series is any series of consecutive integers with the sum of 2000. Let m represent the first term of a millennium series. Determine the minimum value of m. So if you have a sum of consecutive integers, it will be something like this, right? 1 plus 2 plus 3 plus 4 all the way up to some number, dot, 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 n. And do you know or remember how to calculate this sum mathematically? It's n times n plus 1 all over 2. Okay? So they're saying we have some series, and the sum is 2000. So something. 1 plus 2 plus 3 plus 4, like that, all the way up to n is equal to 2000. But it's not that simple because they haven't told us what the first number is. I'm just giving you an example of what it may look like. Okay? But we don't know if it looks like this. This is just a possibility. So they want us to figure out the minimum value of the first term. So if it was like this, the first term would be 1. And we have to figure out, is that the minimum? All right, so I just wanted to give an introduction of how this question works, what they're talking about. So what we need to do is we need to start introducing the letter m. So let's say you have a series of n integers, like that. And the first term is m. That's what the question is saying. So they're consecutive, so this would be m plus 1. The next term would be m plus 2, and so on, all the way up to the last term, which would be m plus n minus 1, right? Because there's n integers. So for example, if there was 7 integers, it would be m plus 1, m plus 2, m plus 3, m plus 4, m plus 5, and m plus 6, correct? 1, 2, 3, 4, 5, 6, 7. That's why it's m plus n minus 1. All right, so I hope you understand that. Now we want to take the sum of this right here. Well, looks like we have to add up all the m's. And how many m's are there going to be? There's going to be n m's. So n m's. All right? Don't get confused. This is straightforward at this point. So now we have to add up 1 plus 2 plus 3 all the way up to n minus 1. So I'll write that out first. 1 plus 2 plus 3 all the way going up to n minus 1. And that's where this formula comes in. All right? So we have first the n m's, and then this whole thing becomes n minus 1 times n minus 1 plus 1 all over 2. Okay? So let's move this up. And they're saying this sum is equal to 2000. Yes, 2000. All right. So we need to work with this. So let's first multiply through by 2 to get rid of that half there. So this becomes 4,000. This becomes 2nm. And the fraction disappears. And this just becomes n because it's minus 1 plus 1. So now let's put everything on one side and multiply this out. N squared minus n plus 2nm minus 4,000 is 0. So n squared, I'm going to factor out an n, and it will be 2m minus 1 minus 4,000. Okay, this is about as far as we can go. So now I need to teach you a trick, or it's not really a trick, it's just a rule, that if you have a polynomial, the sum of the roots are equal to minus b over a. And the polynomial is of the form y is equal to ax squared plus bx plus c. All right? So you take b and divide it by a and add a negative. That's the sum of the roots. The product of the roots is equal to c over a. Okay? So we are going to use those two little formulas to proceed with this question. So in our polynomial, what is b over a negative? Well, b is 2m minus 1, and a is just 1, and of course we got to add this little negative here. And then c over a is just minus 4,000 over 1. Okay? Now immediately when I look at 2m minus 1, I hope you see that it's an odd number, right? 2m is even because you're multiplying m by 2, therefore it's always going to be even, and if you subtract 1, it'll be odd. So that means the sum of the roots are an odd number. So that means that the roots, if you add two numbers and they're odd, one root is odd and the other root is even. That's the only way that you can have the sum odd. Okay? And I'll simplify this. This will be what? 1 minus 2m. Like that. All right. So we've got everything we need to proceed with trying to figure out what is m. Because remember at the beginning of the question, they asked us, determine the minimum value of m. So now what we need to do is we need to make a table. So in my table, I'm going to have 4 columns. The first one is the product of the roots, which is always going to be minus 4,000. So that's going to be easy to fill out. The next column is going to be the possible roots. So we will have to figure those out. Sum of the roots is always going to be of this form, 1 minus 2m. And then I will calculate the value for m. And then we will be able to see what is the possible values for m. All right, so here we go. Product of the roots is always minus 4,000. So I can just fill that in. Possible roots. So two numbers, because there's two roots, that multiply to give minus 4,000. So let's go with extreme case scenario first. How about negative 1 and 4,000? Would that do it? It would do it. So the sum of these roots, well, if the roots are negative 1 and 4,000, the sum is 3,999, right? I just added those two. Now we have to calculate for m. And how do you do that? Well, if you remember, the sum of the roots right here are equal to 1 minus 2m according to our formula. It's not our formula, it's the formula. So I'll just put that in here, 1 minus 2m. And we will use that throughout. So let's calculate. 1 minus 2m in our case is equal to 3,999. Okay? And if you solve for m, you'll get m is equal to negative 1999. All right, so hope you understood how I did that. Let's keep going here. 1 and negative 4,000, that's another possibility. This would therefore give 3999. And 1 minus 2m is equal to minus 3999. And if you solve for m, you will get m is equal to 2,000. Okay, let's keep going. How about 2 and 2,000? Like that. Tempting, but that's wrong. Why? Because, you remember, one root is odd, the other is even. We figured that out because the sum of the roots is odd. So, although this seems mathematically appropriate, it's incorrect. Can't have two numbers that are even. So let's keep going by being consistent with our requirements. Minus 5 and 800, that will work. And therefore this becomes 795. And therefore 1 minus 2m is equal to 795. And solving for m, we get minus 397. All right, 5 and minus 800, that's another one that will work. This therefore becomes minus 795. 1 minus 2m is minus 795. And therefore m is equal to 398. And you have to now figure out another one. 25 and 160, that will work. This becomes 135 as the sum. 1 minus 2m is 135, and therefore m is minus 67. 25 and 160 negative, that will work. This becomes 135 negative. 1 minus 2m is negative 135, and m solves to positive 68. And there's one more, 125, one more pair. 125, 32 negative. This becomes minus 93, and if you solve for m, you'll get a value of m equal to 47. And then finally, 125 and negative 32 is the only other possible set of roots where one is even and one is odd. So this one gives you 93, and 1 minus 2m is 93. So m solves to minus 46. All right, so let's go back and read the question, figure out what they're asking. Determine the minimum value of m. Okay, what is the minimum value of m? Look at all our m's and figure out what is the minimum m. And it looks like the minimum is right here. Minus 1999. That's the smallest value of m, minimum value of m. And then what is the second part asking? The second part asks, determine the smallest possible positive value of m. Okay? So of all the positive values, which one was the smallest? Well, this is positive, this is positive, this is positive, and this is positive. So of all those, the smallest one is this one. So there you go. This is the answer for A, and this is the answer for B. A, B, C, D is a cyclic quadrilateral, as shown, with side AD equal to D, where D is the diameter of the circle. AB is equal to A, BC is also equal to A, and CD is equal to B. A, B, and D are integers, and A cannot be the same as B. Prove that D cannot be a prime number. So a little bit of review, not too much, is when they say cyclic quadrilateral, what does that mean? It basically means that these angles are in a relationship. So B plus D, the angle at B and the angle at D, equal 180. And similarly, A and C, those angles, the angle here and the angle there, also equal 180. Okay, the angles. So just remember that. That's what cyclic quadrilateral means. And then, of course, if you add them all up, A plus B plus C plus D, all the angles, it will be 360. Now, another quick review is something known as the law of cosines. We're going to use that in this question. I think we're going to probably need it at least once. We'll see. We'll take it from there. Law of cosines, what is it? So if you have a triangle, any triangle, does not have to be a right triangle, and you have, let's say, vertices A, B, and C, and I'll label the sides length A, length B, and length C, then it basically has this relationship. A squared, which is this guy right here, is equal to B squared plus C squared. Right now it looks like a quadratic, right? Or not quadratic, a Pythagorean theorem. But because this is not a right triangle, we have to now add something additional. Minus 2BC cos A, where A is this angle. All right? So remember this. You probably already know it. And let's proceed. So now we can use a triangle inside this diagram and the law of cosines. So which triangle are we going to use? Well, I'm going to draw a perpendicular from A to C. And the triangle we're going to therefore use is triangle ABC. Okay? We're going to use the law of cosines on triangle ABC. So what do we have here? We have AC squared, this side that I just drew, is equal to A squared, which is AB, plus A squared, which is BC, minus 2 times A cos of which angle? This angle right here, cos B. All right? So therefore, AC squared is equal to 2A squared minus 2A squared cos B. And you can factor out a 2A squared, and this becomes 1 minus cos of B. All right? So no tricks so far, just the standard law of cosines. Now, at this point, I want you to remember something, that if you have an angle inscribed in a semicircle, it will be 90 degrees. So do we have an angle inscribed in this semicircle right here? Yes, we do. It's this one right here. A to C to D. That angle is inscribed inside a semicircle. And do you remember what that angle will equal? How many degrees? 90 degrees. All right? And that's very helpful. So now, the next step in this question is recognizing that AC, we can use Pythagoras. AC right here is equal to AD squared minus CD squared, right? D squared minus B squared, like that. So now we can proceed. D squared minus B squared is equal to 2A squared 1 minus cos B. This is what we have to now deal with. Now, you might say, well, so far we haven't talked about cyclic quadrilaterals. I mean, it was in the question. Where are we going to actually use it? This is where we use it, at this point in the question. B plus D is equal to 180 degrees. That's a property of a cyclic quadrilateral. So this angle B plus this angle is equal to 180. So therefore, the cos of B is the same as the cos of 180 minus D, right? Because B plus D is equal to 180. So all I did was I substituted B to become 180 minus D. And the cos of 180 minus D is the same as the cos of D. This is just one of those fundamental properties in trigonometry. So we can now make this in terms of D. So this becomes 1 minus cos D, like that. All right? So D squared minus B squared is 2A squared, 1 plus cos D. So what is the cos of D? If you look at this diagram, we can figure that out because we have a right triangle in there. The cos of D would be the adjacent, which is B, over the hypotenuse, which is D. So we can substitute that into here, and therefore we can get rid of this cosine. 1 plus B over D, like that. And then multiply out, you get 2A squared plus 2A squared B over D, D squared minus B squared. Right? There you go. So now we've got to do a little bit more algebra to simplify this. Multiply through by D all the way through, and you get D cubed minus DB squared is equal to 2A squared D plus 2A squared B, like that. And factor out a D, and this will give you D squared minus B squared. Factor out a 2A squared, and you'll get D plus B, like that. And then this factors into D minus B, D plus B equals 2A squared D plus B. And the good news is the D plus B's cancel. So you're left with D times D minus B is equal to 2A squared. All right? And this is about as far as we can go with this equation. Now we have to deal with this. Now remember, the question is asking, can D be a prime number or not? We have to prove that it cannot. So prove that D cannot be prime. So just a little bit of refreshment here. A, B, and D are 3 letters, are integers. So that's definitely something that you need to keep in mind. We also were told that A is not equal to B, and we also know that D is the diameter, so it's greater than A, and D is also greater than B. These are the conditions. So this is going to play an important role in us trying to figure out D and trying to figure out that whether it's a prime or not. So the first thing is, because they're integers, let's start with the smallest integer, D equal to 1. Can D equal 1? Well, no, because if D equals 1, then what's B? Right? D is greater than B, and B will therefore be 0, so this is not a possibility. How about D equal to 2? Can we have that? Well, let's see. Substitute it in and see what we get. If D is 2, we'd have 2 for D. And then how about B? Well, if D is 2, the only possibility for B is 1, because D is greater than B, and both are integers. So I put that in there, 2A squared. So this becomes 2 is equal to 2A squared, and therefore A is equal to 1. Now initially that seems good, but it's not good because this fundamental property is violated. A cannot be the same as B. So this is no good. So that means D has to be greater than or equal to 3. All right? That much I will agree with. But can it be a prime? Can D be? Well, we need to work with this equation here. We got 2a squared is equal to d times d minus b, like that. And therefore, 2a squared over d is equal to d minus b. Correct? Now we need to look at this equation because that's all we have. We have nothing else. So this part of the equation, 2a squared over d, it has to be an integer. Why? Because it equals d minus b, and both d and b are integers. So if you're subtracting one integer from the other, the result will be an integer. So this part will have to be an integer. Now, if that is an integer, then a squared over d has to either be an integer or be able to become an integer if you multiply it by 2. Now here's where we start talking about prime numbers. If d is a prime, then that expression is in lowest terms, right? You cannot make it any lower if it's a prime number. Prime numbers are not divisible by anything other than themselves and 1. And if that is the case, then there's no way you can make this an integer by multiplying by 2. Then this multiplied by 2 will not be an integer because you have to first multiply it by 2 and make it into an integer. Try it. Try plugging in some values and see. It will not work. All right? So that is what they're asking for. Show that d, right here, cannot be a prime. So now we move to the next part of the question, which states, determine the minimum value of d. So our equation was 2a squared is equal to d times d minus b. And we will make a table here. D equals 1. Well, that's not the case. D equals 2. We showed that's not the case. Can d equals 3? No, because 3 is a prime number and d can't be prime. Can d equal 4? Well, we'll see. D cannot equal 5 because that's a prime. Can d equal 6? We shall see. D cannot equal 7, and so on. And I hope we don't have to do too many here. D equals 10 and so on. Hopefully we'll get it pretty quickly. So which one do we start with? We start at d equals 4. If d equals 4, then we've got 2a squared equals 4 times 4 minus b. So this means a squared is equal to 2 times 4 minus b. All right, so we don't know what b is. Well, if d is 4 and b is an integer, b can be either 3, b can be either 2, or b can be either 1. So we've got to figure this out for each of these. So let's figure it out for b equals 3 first. So we got 2 times 4 minus 3, and this becomes 2. A squared is 2, therefore a is equal to root 2. Well, that's no good because a has to be an integer. So that's gone. Let's try b equals 2. And this would become a squared is 2 times 4 minus 2, which is 2 times 2. And therefore, a is 2. But a cannot be the same as b, right? That was one of the requirements of the question. A cannot be the same as b, so that's gone. So now let's try b equals 1. So that would be a squared is equal to 2 times 4 minus 1. And therefore a squared is equal to 2 times 3. So a squared is equal to 6. A is the square root of 6. And that doesn't work because a is not an integer. So none of these work. So that means that D cannot equal 4. All right? So that's no good. So now we got to try D equals 6. If D equals 6, then that means 2a squared equals 6 times 6 minus b. And for the sake of time here, I'll let you do all the b's. 1, 2, 3, 4, and 5, right? Those are the possible values for b, because b is an integer and it's less than d. So you'll figure out for all of these that none of these give integer solutions. No integer solutions for a. Except when b is 3, it will give a equals to 3, but that's not allowed because a cannot equal b. All right? So D is no good. Let's try D equals 8. D equals 8, that means 2a squared equals 8 times 8 minus b. And we've got to figure out this for b equals 1 all the way up to 7. Like that. And I'll let you do this. And if you do, you'll find that the only value that this works and gives integer solutions, where a and b are not equal, is b equal to 7. So for example, you've got 8 times 8 minus 7, which is going to be 2a squared is equal to 8 times 1, and therefore a squared is equal to 4, and a is equal to 2. So it's a very tedious question here. B is 7, A is 2, and D is 8. That's the only possible integer values. And what is the question asking? Determine the minimum value of D. All right? So that's what we did. We determined that the minimum value of D is 8. Now we could keep going, but not necessary to do that, thankfully, because they only want the minimum value, and therefore that is 8.